Hi everyone, this is an introduction video of our WACV paper, Controlling Character Motions Without Observable Driving Source. We will introduce our work following the outline. Synthesizing the character motions based on a given driving source have been a long-studied problem. For example, Balendo generates motion sequences based on a given music. Learning to listen models the facial motion sequence of the listener based on both the audio and the head motion of the speaker. These two works, along with many other works, try to model the semantic respondence between the motion X and a certain kind of input condition C. However, there are many scenarios where the character still needs to be continuously animated without an observable driving source, especially when controlling and synthesizing long and versatile character motions that are lifelike. For example, in the idle state of a VTuber, when there is no interaction and hence not responding to any external signals, it's indispensable to control the motion behaviors to make it look natural. Our paper aims to solve this problem and model the equally important PXT given the past motion sequence. We argue that this seemingly trivial problem is actually challenging for the following reasons. First of all, conventional autoregressive method will cause the out-of-distribution issue because of the error accumulation. Secondly, insufficient diversity will become a fatal issue when we try to produce infinitely long sequence. Lastly, there will be the undesired periodic pattern issue along the time when the sequence goes long enough. To address the above challenges, we officially define the problem of controlling character motions without a driving source. Our algorithm consists of three parts: a quantizer that encodes a continuous motion sequence into a discrete token sequence, a low-level policy to decode the token sequence, and a high-level policy to generate the token sequence. To tackle the out-of-distribution issue, we discretize the continuous feature space using VQ-VAE. This discrete token space serves as both the input space of the low-level policy and the output space of the high-level policy. Directly decoding the token sequence back into the continuous feature space using the VQ-VAE decoder will cause a lacking of diversity issue. Therefore, we instead employ a low-level policy to decode the token sequence. The low-level policy takes three parts as input: the token, which is provided by a high-level policy, a random noise for diversity purpose, and the past motion sequence for continuity. To train the low-level policy, we deploy a reinforcement learning framework such that the policy considers not only the current time step, but also the long-term quality. The reward also consists of three parts. The realistic reward corresponds to whether the generated sequence looks natural. We use a gain loss for realisticity. The diversity reward encourages the policy to produce diverse outputs given different noises. It is represented as the L2 distance between the reconstructed and the input noises. The correspondence reward stands for whether the output frame hits the specified input token. We use the VQ-VAE encoder and quantizer to transform the output frame back into the token space. If the output token turns out to be the same as the input token, the reward is 1, otherwise the reward is 0. We use PPO to train the low-level policy network. Generally speaking, the high-level policy should take both the driving source C and the past frames as input. In our setting, we focus on the scenario where the condition C is an empty set. We try both an autoregressive high-level policy and a random prior policy. We then go to the empirical result part. We first visualize the codebook on both the Trinity gesture dataset and the VTuber Emoca dataset by feeding the codebook into the VQ-VAE decoder. Here are some codebook examples on both datasets. We then show how our low-level policy can decode the specified code into a natural and diverse sequence. The first line shows an example codebook on the Trinity dataset. We select the first token and generate a 3-second sequence, which is like this. We also show the detailed frames in the sequence. We can see that the low-level policy generates a natural sequence based on the provided task token. All the frames are close to the input token, but they are not completely the same. The whole sequence looks natural. We then select the next token and continue to generate the sequence. This is the generated sequence and the detailed frames. In the beginning part, the sequence naturally transits from the last task token to the new selected token. Then, the low-level policy generates a natural sequence based on the new provided task token. We can continuously select new task tokens to control the generation of the low-level policy. The complete generated sequence on Trinity dataset is like this. We then combine our low-level policy and high-level policy together to generate the end-to-end result and compare the results with these baseline methods. We first compare our algorithm with a vanilla autoregressive model. These three videos correspond to our method, the autoregressive model, and a reference ground truth video from left to right. On the Trinity dataset, it is clear that the autoregressive model produces still an out-of-distribution result. This is the result on the VQ-VAE dataset. The autoregressive model produces periodic pattern. We then compare our algorithm with both clip-level VQ-VAE and frame-level VQ-VAE. This is the result on the Trinity dataset. The clip-level VQ-VAE has less diversity. The hands are almost always around the waist of the person, while the frame-level VQ-VAE produces jittery results. Finally, we compare our algorithm with AMP and ASC. This is the result on the Trinity dataset. AMP has a periodic pattern, though the first 5 seconds looks reasonable. We further plot the consecutive 40 frames since the 5th second. The first 2 rows are similar to the last 2 rows. Note that both AMP and ASC are not controllable, meaning that we cannot specify which token to use since they do not have a discrete token space. This is a table of quantitative evaluation on 3 datasets, namely the Trinity Gesture, ARST++, and VQ-VAE. Our methods achieve the best performance among all the algorithms. The autoregressive algorithm completely fails, since it drops into a fixed point very quickly. Both frame-level and clip-level VQ-VAEs suffer from poor performance because they cannot produce diverse trajectories. Using reinforcement learning clearly upgrades the performance, since it considers the long-term quality. Thank you for watching the video, and feel free to contact us if you have any questions.